Assalamualaikum warahmatullahi wabarakatuh. SMQ 3093 Numerical Solution of Linear Algebra Assignment 2 from Group A3. The lecture name is Dr. Nur Akmal binti Muhammad. Okay, for the question. Find the least square solution of linear system. Given AX equal to B, where A is this and B is this. Okay. Okay, for the least square solution, first we take a transpose of A, and then A transpose we time with A. And then the least square solution is x equal to A transpose time A, -1, time A transpose time B. Now we find the A transpose A, -1. Augment, augment with A 3 times 3 identity matrix. Okay, swap metric row R1 to R2, and then we cancel leading coefficient in row R2 by performing R2 minus 39 over 59 times R1. Cancel leading coefficient in row R3 by performing R3 minus 93 over 112 times R1. And then we cancel leading coefficient in row R3 by performing R3 plus 257 over 314 times R2. And then we multiply metric row by constant 2198 over 19463 times R3. Cancel leading coefficient in row R1 by performing R1 minus 173 times R3. Then we multiply metric row by constant negative 8 over 157 times R2. And then we cancel leading coefficient in row by performing R1 minus 189 times 2. Next, we multiply metric row by constant 1 over 112 times R1. Okay, we got the inverse metric is on the right of augmented metric. Then we multiply A transpose times A, -1 with A transpose. And then what we get is this. Then we find the x equal to A transpose times A, -1 times A transpose B. And then we got the final answer. So the x1 equal to 29,581 over 19,463. X2 is -21574 over 19463. And we got the x3 is 20844 over 19463. That's all.
Assalamualaikum and good afternoon to our lecturer. She is Dr. Akmal. So today I, Muhammad Asri will explain about how to use coding with Wolfram Mathematica in question 1. So today we will use least squared method for question 1. Then based on the question, we will insert for this coding using matrix form A equal to bracket 269 786 453 and 787 387, and we close the bracket. So this comma is function to separate between the row and between each entry. So and this comma is to separate each entry. So Then after we insert this coding, we just need to press shift plus enter, and we get the output in the matrix form. So for the matrix form B, we will use same as matrix form A, and we will press shift enter to get the matrix form. So we get 7, 6, 8, and 2. Lastly, for we get the x1, x2, and x3. We just need to enter this coding, least square bracket A time B. So we press shift and enter, and we get the output for the x1. This one is x2, and this one is x3. Thank you.
Okay. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zuhair Kahimi bin Muhammad Nasri. Okay, for today, I would like to share about Gram-Smith solution. Okay, let's start it. So, if we look at this, okay, we have some question, which is by using Gram-Smith, find the orthogonal basis, and after that, orthonormal basis for the call A. Call A, which is it's mean that matrix A. Okay, so okay, we have matrix A equal to span, which is we have 3 by 4 matrix. Okay, so for the column number 1, we have 2, 7, 4, 3. Okay, for the column number 2, we have 6, 8, 5, 8. And for the column number 3, we have 9, 6, 3, 7, which is x1 if is for the column number 1, x2 is for the column number 2, and x3 is for the column number 3. So, firstly, what we have to do to find the orthogonal basis, we have to let vector 1, which is vector 1, we have 2, 7, 4, 3. Okay, so based on this, we got the partial basis x is equal to 2, 7, 4, 3. Okay, we don't have to calculate for the vector 1. Okay, and then we proceed for the vector 2. Okay, we let vector 2, which is 6, 8, 5, 8 minus projection x 6, 8, 5, 8. Okay, so to calculate this, we use the formula this one. Okay, so by using the formula, okay, we entry all the numbers, which is vector 2, 6, 8, 5, 8 minus, okay, 56 over 39. Okay, vector 2, 7, 3, 4. Okay, so we divide both sides by 39. Okay, so after that we got this, and then okay, after we got the last calculation, we will got the partial basis for the x vector 2. Okay, which is 1, 2, 2, negative 8, 86, negative 29, 144. Okay, so and then what we have to do is we have to find x3, which is to find x3 we will use the vector 3. Okay, so we have 6, 8, 5, 8 minus projection x, which is 9, 6, 3, 7. Okay, So after that we will got this form. Okay, and then after we got this form, we will use this formula to calculate. Okay, so okay, we entry all the numbers. Okay, and then okay, 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 and then the lastly we will got the vector 3 is this. Okay, so so after we finish the vector 3, we have run all the solution for the orthogonal basis, which is we got okay 2743 for the vector 1, okay 122 negative 18 negative 29 144 for the vector 2, and then the last vector is this. Okay, so after we finish done find the orthogonal basis, we will find the orthonormal basis. Okay, to find the orthogonal basis, what we have to do is we need to normalize this at the end. Okay, so at the end for the orthonormal basis, we have done. Okay, so by using this formula Q1, Q2, Q3, okay, and then we use entry for the formula. Okay, we also have magnitude square root x power 2 plus y power 2 and plus z to the power 2 for 3D vector. Okay, so by using this formula, okay, we entry all the vectors number, which is we will refer to the orthogonal solution that we have finished. Okay, so the final orthogonal solution, so we entry and then we got the solution for the orthonormal basis. Okay,
Okay, next we will look at on how to solve this problem by using Gram-Schmidt to find the orthogonal basis, and after that we're going to find orthonormal basis by using the Wolfram Mathematica. So based on the question, we first define the in a metric form, which is this is x, this is y, and this is as a z, column by column. So we will get this one. So metric form for the s, we put s equal to open bracket 2, comma 7, comma 4, comma 3, and then close bracket. So and then we press the shift enter, and we will get the output as you can see in the screen. So we do this for the 3 columns, and then we are gonna find the orthogonal basis for the vector s. So we have to define the metric x, y, and z. We can define the orthogonal basis for the vector 1. So the vector 1 is equal to the partial basis of x. So we put it as a v1 equal to x, and then shift enter. Okay, next we will define the orthogonal basis for the vector 2, which is y minus projection of y onto the partial basis of x. And we put this command, and then we press the shift enter, and then we will gonna find the orthogonal basis for the vector 3, which is z minus the projection of z onto the partial basis of x, which is z minus the projection of z into x. And then we will put the comment that you can see in the screen. And then we just press shift enter. Okay. Now, once we get the orthogonal basis, we now can find the orthogonal basis. How to find the orthogonal basis? Okay, let's say we define the matrix as A. So A equal to, we put the common here, which is orthogonalized, and then we put the orthonormal basis V1, V2, and V3. And of course, we want to see the answer in a metric forms. So we put the such metric forms. Then we press the shift enter and we get the answer. You can compare this answer by using the manual calculation. Okay.
Hi, Assalamualaikum, and now we can jump into the next question, which is we need to find our x by using QR factorization. So first thing first, we need to have our Q metric. So where can we get our Q metric? So first thing we had to know the metric is orthonormalized vectors, which is we can get from Gram-Schmidt result, and from the Gram-Schmidt result we can get our Q with this value. And after we get our Q, we had to transpose our metric Q. So this is our Q transpose. And after that, we need to find our R. So we can use this formula, which is Q transpose multiplied with metric A. And this is our R. And after we get our R, we need to inverse it, which is we need to find our R inverse. And this is our R inverse. And after that, we need to find our Q transpose multiplied with B. So Q transpose substituted with metric Q transpose with metric B, and we get our Q transpose B. And finally, we can get our x by using this formula. X equal to R inverse Q transpose B. So from the last thing that we all do is we find the R inverse and we find our Q transpose B. So we just had to substitute our value into this formula. And after we substitute with A equal to R inverse for the first metric, and the second metric was Q transpose B, and after that we can get our x, which is the first x that we get is 1.519862, and the second x is negative 1.108465, and the third x is 1.070956.
Next, we want to solve x using QR factorization for this problem using mathematical programming. So first one, we need to define these two metrics, which is metric A and metric B. So we put the command here, matrix form, in a bracket A, which is for matrix A, and we put the entry row by row. We separate the entry and each row with the symbol comma right here, and then we press shift enter and we'll get the output in a matrix form. Same goes to matrix B. We put the command here and then we press shift enter, we will get the output like this. And then from the QR decomposition of matrix A, we can find the QT, which is Q transpose, and R, which is upper triangular matrix. So we put command here in the braces, QT, comma R, close braces, equal to QR decomposition of matrix A. And then we press shift enter and we'll get the output. And then we want to recall the QT in a matrix form. So we put the QT double slash matrix form and press shift enter and we get the output. Same goes to R. Okay, next we want to solve the value of X. So we put the command using the equation R inverse multiplied by QT multiplied by matrix B. So we put the command here x equal to n, which is we want the answer in a numerical value, open bracket inverse open bracket R close bracket, dot, which is symbol for multiply, QT multiply B close bracket, and then we press shift enter and we will get the final answer.